So back in geometry, you all studied something called oblique triangles, and this is where our lesson begins, okay? So what's the definition of an oblique triangle for us? Anybody remember? Back in geometry?
It's like over 90 degrees.
Yeah, that's one way. That's one. One of them is. So you're on the right track for sure. So oblique triangle means no right angles. Okay, so in that case, if there's no right angles, we can either have an acute oblique triangle or an obtuse oblique triangle. And for us, the way that we describe these oblique triangles is going to be as follows. Each oblique triangle has to have three angles. We're going to call those angles capital A, capital B, and capital C. Doesn't matter really where we put them. Capital A, capital B, capital C. These are going to be the three angles of our triangle, of our oblique triangle. And we're going to describe the sides of our oblique triangle in terms of the angle it's across from. So what I mean by that is as follows. If this is angle A, then the side of the triangle that is opposite angle A is going to be called side little a. Fair enough? Okay. The side that's across from angle B is going to be called little b. And then the side that's across from angle C is going to be called little c. So it doesn't matter how you set them up, as long as you have that ratio in proportion, right? So A, B, and C. So across from A, across from B, across from C, little c. So this is our obtuse oblique triangle, and this is our acute. There we go. Oblique triangle. That's where our study begins. So we actually solve oblique triangles, either obtuse or acute, using the law of sines. Okay, so when I have the word solve in quotation marks there. So the word solve, what do I mean by the word solve? Anybody know? To solve, what does it mean to solve a triangle? Yeah, very good. You need all three sides, right? And you need all three angles. If you can tell me all three sides and all three angles to the oblique triangle, that triangle is considered solved. So that's what it means to solve a triangle, oblique triangle. So using the law of sines. Okay, then what the heck is the law of sines? So we're going to actually develop it right now. So draw yourself any oblique triangle. There's mine right there. I'll call this A. I'll call this B. I'll call that C. And then I'll label it as little a over here, little b, and little c. Any old standard oblique triangle, no big deal. We're going to drop an altitude. What's an altitude again? A line from vertex C all the way down perpendicular to the opposite side. And I'm going to call that altitude h. I have to call it something, so I might as well call it h. All right, now I have a right triangle inside my oblique triangle, right? So now, what can you guys tell me from your trigonometry? You can tell me something about the sine of angle A. What is it? If you look at that right triangle, what is it? Very good. It's equal to h divided by b. So therefore, h is equal to little b times the sine of angle A. You guys agree with that? You guys on board so far? Okay, I wonder then if you could tell me something about the sine of angle B. Look where angle B is. It's over here. Can you tell me something about its sine? What is it? No. Use that right triangle. This is the right triangle as well, right? Very good. The sine of angle B has to be h divided by a. So therefore, h must be little a times the sine of b if I, cross multiply both sides by a. So therefore, check this out. If h is equal to b sine a, and h is also equal to a sine b, then what can you say about those two things? They must equal each other. So therefore, I can write the statement down. B times the sine of a, so this part right here, must equal this part over here, huh? A times the sine of angle b. Okay? Now, I'm going to do something kind of tricky, but legal nonetheless. Okay? I'm going to divide both sides by sine A times the sine of b. Divide both sides by sine A times the sine of b. And does anything neat happen for us? On the left-hand side, this sine A, that sine A cancel out. On the right-hand side, this sine B and that sine B cancel out. And I'm left with something. What am I left with? B over sine B is now equal to, what's on the right-hand side, everybody? A over the sine of A. Now, I have a proportion there, right? If I were to drop another altitude, say from here, right, I could similarly prove that C over sine of C is also part of that proportion. So therefore, this right here is the law of sines. That's not so bad, huh? And we just actually proved it. All right? The other way to represent it is like this. A lot of students like it like this. Sine B over B equals sine A over A equals sine C over C. This is also acceptable. Either one of these will work. Both of these are considered the law. All right, so in this example, here's a very straightforward one. We want to use the law of sines to solve this triangle, right? It's an oblique triangle. So therefore, in order to solve it, I'm going to need some information. I'm going to need all three of my angles, A, B, and C. And I'm going to need all three of my sides, A, little b, and little c. This is what I need. Now, some of this information has already been given to us in the problem, right? Do I know the angle for A? What is it? That's 46 degrees. Okay, no problem. Do I know anything else? C is what? That's 63 degrees. Good. Do I know anything else? C is what? 56 inches? 56 inches. Okay, those are the ones that were given to me, right? Now, we can infer, we can figure out what that one is right away, right?
71.
Yeah, why is that one 71? Very good, because all of them got to add to 180, right? So that one's got to be 71. So really, this isn't so bad, huh? Really, all we have to do is figure out that side and that side right there. That's not so bad. So in order to solve this, we need to figure out those two, and then we'll be good to go. The only actual proportion that I know, right, or actually the ratio that I know is something with C, right, side C and angle C. So I'm going to start with that one. So I'm going to say what I know. I know that the sine of 63 degrees divided by the opposite side, which is 56 inches, has to be, now I have to find A or B. It doesn't matter which one I pick. I'm just going to go with A for now, okay? Has to be the sine of 46 degrees divided by little a. Now I have a proportion, right? I have two ratios set equal to each other, right? So all I have to do is solve this little proportion. No big deal. So therefore, how about this? If I do cross product here, I'm going to get that a times the sine of 63 degrees has to be 56 times the sine of 46 degrees. Therefore, now I'm going to divide both sides by the sine of 63. I'm going to divide both sides by the sine of 63. So I'm going to get A is equal to, when I plug this into my calculator,
Why would you divide both sides?
because I want to solve for A, don't I? So I'm going to divide both sides by that. Have it cancel out. You on board? Okay, so let's take our calculators out.
What happens if you put sine of 63 in your calculator first and like sine of 46 and then
Let's try it. This is the way I do it. I do 56, and then I do sine 46, right? And then I just push enter to get my numerator, and then I divide by sine 63. This is how I do it, and it works every time. That way I keep everything separate in my calculator. So I'm getting 45.21, and this is going to be inches. So now I'm do it the other way, and see if you get 45.21. So this is now 45.21 inches. Am I done? No, I have to do one more, right? No big deal. Okay. So I'll do it on this side, and I'll change colors just so we can see. So the one that I know is this. I know that the sine, 63, all over 56, now equal to the sine 71 degrees all over little b. Therefore, when you run this through your calculator, b has to be 56 times the sine of 71, all divided by the sine of 63. So when I did it, I got 59.4. Can someone else verify that? Let me get that. 59.4 inches right there. So there are three cases in which using the law of sines to solve an oblique triangle is appropriate. There's three cases for them, right? The first one is side, angle, angle, or some people like to call that angle, angle, side. So remember back in geometry when you were actually using these triangle congruences to show that two triangles were indeed congruent? One of them was angle, angle, side. Give me another one that you remember. Angle, side, angle. Very good. Angle, side, angle. That was one of them. Give me another one.
Side, angle, side.
Side, angle, side was one of them, but we do not use the law of sine for that one. We use the law of cosine for that one, and that's tomorrow's lesson. Okay? So for these, we have this one. Was there another one though that you had to stay away from? Yeah, there it is. Okay. Angle, angle, side, side. Okay. So these first two, right? These first two we use law of sine for, and this is kind of normal. All right? But this one, there was something special about that one, right? And what was it in geometry? Remember angle, side, side? Remember that one? Were you ever allowed to use that one? No, why not? Anybody remember why not? Because it was invalid. Do you remember why? Because it spells a bad word, right? That's the main reason. Okay, this has a special name. This is called the ambiguous case.
Two answers.
Yes. All right. This is called the ambiguous case. So when you are given an angle and two sides of a triangle in that order, an angle and two sides that are next to each other, that's called the ambiguous case, and three things can happen from the ambiguous case, which is why you were never allowed to use it in geometry. So when you're given angle, side, side, and you're using the law of sines, you can either have one triangle, two triangles, or no triangles. And we're going to talk about each of those cases individually today. Okay? So you use the law of sines when given oblique triangles and either side, angle, 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 side, angle, or angle, side, side. Angle, side, side, knowing that one is a specific, special, ambiguous case with three possibilities from it. And we're going to talk about each of those today. Okay, here's a sort of a standard example that the book might throw at you, or some information that we would know. Notice that there's no picture here yet. You have to know how to draw the picture correctly in order to know whether to use the law of sine or law of cosine when we get there tomorrow. So then let's go ahead and draw the picture and figure out what we've been given. We know that if I call this A, I call this B, and I call this C, I know something. I know some things, right? I know that this is 50 degrees. I know that B, which has to be opposite this one, is 76 feet. And then I also know that C up here is 33.5 degrees. So ladies and gentlemen, I've been given an angle, a side, and an angle. Right? So this is angle, side, angle. So what do I use? If I'm given angle, side, angle, what do I use? I use the law of sines because there it is right there. I've been given angle, side, angle. So I know that I use the law of sine for this triangle, right? Even though it's part of this lesson, just saying in general, if you didn't know, that's how you'd be clued in. And since it's an angle, side, angle, it's a normal case, I don't have to worry about the ambiguous case. So therefore, I can just proceed as I normally would, knowing that I have angle, side, angle. Sweet. Okay. So what do I know? Oh, can I get this one? I sure can. What would that one have to be? Very good. 96.5 degrees. So therefore, that's the one I'm going to start with, right? So here we go. I'm going to say the sine of 96.5 degrees, all divided by 76, has to be the sine of 50 degrees, all divided by side A. Okay, can I have this table right here, you girls? Can I have you girls figure out side A? Like maybe these two tables, and then the three of you, the girls and the guys in the front. Can I have you do the other one? We'll set up this one. The sine of 96.5 degrees, all over 76, has to be the sine of 33.5 degrees all over side C. Cool. So we just verified A was about 58.6 feet, and then C was about 42.2 feet, and we're all good. All right, the rest of our day is going to be devoted to this idea of the ambiguous case. And you have to consider the ambiguous case whenever you've been given two sides and an opposite angle, or angle side side or side side angle. And this is that one case where in geometry you were not allowed to show that two triangles were congruent because of that, and we're going to show you why. I said earlier there's three possible situations here, right? The first one is there's only one triangle that you could ever find with this. The second one is there's two triangles that you could ever find from this. And then three, there is no such triangle that could be made given the angle and two sides. So you have to figure out which one this is. And I'm going to give you an example of each one and what to look for each one. So this is all going to be under the same box. Let's take case number one. Let's say we're talking about one triangle. All right? I'm going to assume that we don't know that we're looking for one triangle. I'm going to show you how to get it and solve for it. So these are our three cases. We're going to talk about each one at a time. Let's start with one triangle. Number three, no triangles. That's the easiest one, so we'll save that one for the last. Okay? So I'm going to move this up. In the case of given one triangle, here's the setup. Angle A, let's take about, for example, is 43 degrees. Angle B is, I don't know. Angle C is, I don't know. Side A is, let's talk about 81 inches. Side B is 62 inches. Ooh, look at that, crazy. Hey, Mark, that's you. Sweet. Awesome. And side C is, well, I don't know. All right? So, taking a look at this, it's kind of hard to tell without drawing the picture if you're even given angle side side. So I always just go out and draw a picture. Here's A, here's B, here's C. This is 43 degrees. Right, across from this is 81 inches. Across from B is 62 inches. So, taking a look, I have, an angle, then a side, and then a side. So I have angle, side, side. Therefore, I'm going to be talking about the ambiguous case. So I have to consider the ambiguous case. All right, now that I know that I'm dealing with the ambiguous case, here's the strategy. See this other part here, B and C? How many degrees are left over in that triangle, given the fact that 43 of them are already accounted for? Very good. You have 137 degrees left over. This is what I call the leftover piece. You only have that much more, those degrees, to be split up between angle B and angle C. Is that true? Okay. So that's going to be an important number. I'm going to highlight that for us. We're going to come back to that number in just a minute. Keep in mind we only have 137 degrees left over to spare in that triangle. And I know I'm dealing with the ambiguous case, so here's the process. So the only one that we know for sure is this ratio right here. So I'm going to start with that one. So the sine of 43 degrees divided by 81 has to be the sine of angle B, which I don't know what that is, divided by 62. Okay? What am I solving for in this proportion? Or this ratio? Huh? Oh, angle B, not shut up, Sarah. That's what I want. I want angle B. So I'm going to move this up. I'm going to use some cross product here. I'm going to say 62 times the sine of 43 has to be 81 times the sine of B. Everybody on board so far? Okay, so moving right along, I get the sine of B is now equal to 62 times the sine of 43, all divided by 81. Still on board with me? Okay, therefore, the sine of B is equal to, let's plug this into our calculator. What do you get when you plug 62 sine 43 divided by 81 into the calculator? Good. You should get 0.5220. Okay? What does that represent? Is that the angle? No, that's the ratio of some angle whose sine is that, right? So how do I get b then?
Inverse sine.
Very good. I'm going to take the inverse sine of 0.5220. This is going to give you two answers, and I'll explain why there's two. Give me the calculator that will only give you one of them. What will it give you, Alan?
31.468.
31.468. So how about 31.47? You guys cool with that?
Yeah.
Okay, 31.47 degrees. All right? So now we have to remember our trig. Okay? And I'm going to move over here to show it to you. Think about the unit circle. Okay? Here's 0. Here's 90 degrees. Here's 180 degrees. Okay? Now, can you draw for me 31.47 degrees in standard position? What quadrant would it be in? It would be look something like this. Like for the sake of argument, this is 31.47 degrees. You guys cool with that part? Okay. So now, the sine of 31.47 degrees is equal to this value. Is that true?
Yeah.
Okay. There's another angle whose sine is equal to that value as well.
Oh, it's the reference.
It's the reference angle. Awesome. Yes. So there's another angle, right? Sine is positive in quadrant 2 and 1, right? All students take calculus. So therefore, we need to then figure out what this angle is here, and it's the reference angle to 31.47.
Isn't it just 180 minus 31?
Yes, it is, synonyms. It's 180 minus 31.47. What would it be?
148.53.
Very good. Awesome. So 148.53. Now your calculator will only give you one of them. Okay? But, ladies and gentlemen, there are two angles. The first one in quadrant 1, the second one in quadrant 2, whose sine is that ratio of 0.5220 when you simplify. Okay? So now, very good. Now this is where we go back to how much we have left over. Check it out. We only have 137 degrees left over, right? So therefore, can it be the 148.53? No. This one is too big. You would continue on solving with that one only. All right, here's two triangles. Well, first of all, I don't even know what I'm dealing with here, so I'm going to draw a picture. I'm a visual kind of guy. So here's A, here's B, and here's C. I know this is 40 degrees. I know that across from this is 54 feet. And the across angle B is 62 feet. So I am dealing with an angle side, side. Shoot, I have ambiguous case, right? So angle, side, side, ambiguous case. Good, let's go figure out that leftover piece then. Okay, how much do I have left over to spare? Yes, I have 140 degrees left over to spare. Okay, that number is going to be very important in just a second, once we get there. So 140 degrees left over. The only ratio that I know deals with A, so I'm going to go ahead and use that one. So I'm going to do sine of 40 degrees divided by 54, using the law of sines, equals the sine of angle B divided by 62. Therefore, the sine of B, when I plug this all into the calculator, I get 0.7380. I'm just speeding up the process for you guys, right? So therefore, B is equal to the inverse sine of 0.7380. Give me the two angles. I'm going to show you right now. Because both will work, yeah. So give me the what's your calculator say when you plug in inverse sine of 0.7380?
47.56.
Okay, 47.56. Now remember, right? That's the one in quadrant 1. 47.56. How do you get the one in quadrant 2?
Do that 180 minus 40.
Very good. And what do you get? 132.44. Okay, so check it out. There are two angles, namely these two are here, 47.56 and 132.44, whose sine is equal to 0.7380. And check it out. Both of those angles are smaller than your leftover of 140. Therefore, both of them could work. Okay, see how that works?
So you solve for both.
So then you solve for both of them. That's absolutely right. So you would continue on by saying, shoot, now I have two triangles. So if I take this one and I solve it, I would get A, B, and C, and little a, little b, and little c. Or if I take this one and solve it, I would get A, B, and C, little a, little b, and little c. So I've already solved these for you ahead of time, just to show you. So this stays the same in both cases, 40, 40. Little a was 54 feet, 54 feet. Little b was 62 feet, 62 feet. So check it out. Two different triangles that share an angle and two sides, right? But the other three pieces will no way match. Therefore, they could never be congruent. Therefore, angle side side was not one of the ways you ever proved in geometry two triangles were congruent. So if I would continue on with this one and say this was 47.56, I'd get an answer here and an answer here. If I continue on with this one and got 132.44, I get a different answer there and a different answer there. So collectively, that's what our answer would look like. Okay, here's the setup for the last one, the last option, right? Maybe there's no triangles possible with ambiguous case. So I'm going to go ahead and draw what I've got, what I know. Here's 75 degrees. Across from that is 51 inches. Across from that is 71 inches. So I have been given an angle, a side, and a side. Shoot. Okay, angle, side, side. Therefore, I'm dealing with the ambiguous case. Let's figure out the leftover piece. How much do I have left over?
105.
I have 105 left over. So the only ratio I know is here. So let's start with that one. Sine 75 degrees all over 51 has to be sine of B all over 71. Therefore, the sine of B, once you actually calculate it out, becomes 1.30 when you do that math. So therefore, B is equal to the inverse sine of 1.30. So let's punch in our calculator the inverse sine of 1.30. So second inverse 1.30. And do you guys get what I get? You get an error. An error message. Okay? The reason you're getting an error message is because there is no angle whose sine is 1.34. This is an error. Because if you think about it, the sine graph lives between 1 and -1, right? So therefore, the domain when I take the inverse of that thing is going to be between 1 and -1. This is too big. So therefore, it must be the case that no triangle could ever be created given those three constraints. So if you get an error message in your calculator, or your domain for your inverse sine is outside of 1 or -1, no triangle could ever be constructed. And that brings us to the end.